All right, so now what we want to look at are what we call bivariate relationships. We want to look and see really if there's a relationship between two variables here. In this case, we'll look at continuous variables here. So really when we're looking at uh, bivariate relationships, what we're really looking at is association. Right? We want to know, is there some association between these two variables? So we want to see if two variables related to one another. Here, what we want to know is how can we measure, right, the strength of this relationship, right, between those two variables. And, we also would like to be able to model this particular relationship here. So the strength here, we'll measure this with correlation. And the model, right, is what we'll look at regression here. So this is what we look at. And so really what we're doing is just some simple modeling with the regression here. So again, if we want to see if two variables are related, we can do so graphically and we can do it analytically. And really it's recommended that we do both. So first we would like to look at things graphically. And so with two variables or two quantitative variables, really we look at is the scatter plot here. And this is just a graph where we plot the pairs of data. Here, where again each pair represents a point on the graph here. So again, here I have a data set. I've got some variable x, some variable y. Here we get the various values, and again, these values here, these are all paired together here. So suppose each of these came from the subjects. Subject A, B, C, so on. Here all the way down to subject J. Here, so they each have a value for x and for y. And so we want to see, is there an association or some type of relationship between x and y. So here we're doing our scatter plot. Here, so down here on the horizontal axis, right, this is our x, the vertical axis is our y, so we're plotting the points. Here's 1, 1, here's 2, 5, and so on. So again, we look at this scatter plot, and it does look like there's some type of relationship. Right, as x is increasing, then y is increasing here. So what we want to do is see, can we, model this relationship or find out what the strength of this relationship is. Right? So here's another example. We get two variables, x and y here, and now we look at the scatter plot for these two variables, and again, x is still here on the horizontal, y on the vertical, and so now we see kind of much different shape than we saw with the previous example here. So again, we see this type of relationship. It goes down here, then it starts to increase and go up. All right. So again, this is a much different relationship than we saw here previously, where as x went up, y went up here. So really, as x increases, y decreases at first, and then it increases here. So this is another type of nonlinear relationship we can have between the variables here. And now this is a much larger data set here, and this is a scatter plot here where this, on the horizontal axis, this is the number of cigarettes that someone smokes per day. Vertical axis, that's the carbon monoxide level here. So when we look at this scatter plot here, there does seem like there may be a relationship here as, as the number of cigarettes per day increase. Looks like there's some increase in the carbon monoxide level here. So again, this is a much more realistic kind of scatter plot you may come across in practice here. Okay, and again, when we look at this here, another good reason for looking at a scatter plot is we can see if there are any outliers in the data. And so here we've got two values. Again, these are really far from all the other values, right? This one here, the carbon monoxide's up at 1,000, and the next highest one is here about 700. So that one's obviously, well, not obviously, but it is quite a ways away. And then this outlier here, again, we have a low carbon monoxide level, but number of cigarettes per day is 90. So if we were to look at this, we checking to see if perhaps these are typos here in terms of data entry. Just because this number here, this 90 cigarettes per day, seems unrealistic, so we'd want to check that. And maybe the carbon monoxide level here is close to 1,000. It may be possible. Okay, so when we talk about measures of the strength of the relationship, how do we measure the relationship? One measure we can look at is what we call the covariance, right? And this is just a measure of how two variables, x and y, typo, right? How two variables, x and y, vary relative to each other. So this is our formula for the covariance, right? This is how we denote covariance. You may see it the subscript xy, or you may see it covariance and then xy in parentheses here. But what we take each value, subtract its mean, right? Take all the x values, subtract their mean, take the y values, subtract the mean, find the pairwise products here, add these together, divide by n minus 1. So again, this is similar to variance, right? Except with variance, what we just used x and x here. So again, covariance here is the measure of x and y and how they vary relative to each other. And covariance, again, this can be positive or it can be negative here, depending on the relationship here. And so to see the covariance here, this gives us a numeric measure, but it still is good to look at the scatter plot for both of these, for the covariance here. So if I have positive covariance here, so this is, right, if I have positive covariance, right, what we'll see in terms of the scatter plot here is you'll see points here and then some up here, right, in these two quadrants here. So maybe some along here as well. So you see that, as one increases, the other one increases as well, right? Nice positive relationship there. For the negative covariance, we'll see something a little bit different. We'll see, but in this case, it's going to go in the opposite direction, down to the right. So this is our something that we see, kind of a negative covariance here, right? In this case, so obviously this is indicating a type of relationship right, between these two variables here. Again, these aren't always the case. We may see if there's no relationship right, between the two variables, is we'll just get a random scatter of points and all around the graph here. Right? No particular pattern is obvious there. So here, we're seeing a relationship between the two variables. Here, whether it's positive or negative, or if it's none, then you just kind of see just a random scattering of points there. Right? So now, again, we look back at these two data sets we looked at earlier, and if we want to calculate the covariance here, then to calculate the covariance, I'd need to find what the mean, right, for the x's here, the mean for the y's here, then here to get the covariance, then I'm going to need to do what, x minus x bar, right, y minus y bar for each of these values. So I'd have 1 minus whatever this mean is, I'd have 1 minus whatever y bar is here, and then I'd multiply these together, right, so then add those up, and that's going to give me my numerator, and then divide that total by n minus 1. Here, same thing with this other set of values. And here, when we do this, we actually get what, that the covariance is 20.5 for this first one. And for the second set of data, here we have what the covariance is 7.05 in this case. So again, these are both positive here, but remember the graphs of these two. This one here, was a nice linear one. This one over here, it's something that kind of went down and then went up over here. Right? And so again, this is a large covariance, this one, relative to this one here, right? 23 times larger than the 7. So, what does this tell us, well, we look at the scatter plot here, we have a positive covariance here, and even though we had a positive covariance here, we're not seeing really a relationship where they're both kind of increasing at the same time here. So what we actually want is some way to kind of standardize these values so we can compare, right? And to do that, what we actually do is we calculate what we call correlation, right? So in the statistics, again, we talk about correlation, and a correlation just means that there's some type of relationship between two variables here. And there's different measures of correlation. The main one that we'll focus on is the Pearson correlation, and this is the most common one. This is when people talk about correlation, usually they are referring to the Pearson correlation. And I'll briefly talk about the Spearman correlation. It is mentioned in the text, but I'm not going to really get into it there. Okay, so when we talk about correlation, usually we're talking about Pearson's correlation. And technically this is Pearson's linear correlation coefficient here, and the keyword here is linear, right? And what this is a measure of the strength of the linear relationship between two variables here. So, are these linear related? As one goes up, does the other one go up, or as one goes up, does the other one go down? And not only that, but by the same amount each time. So again, remember, we'll look at the linear relationship here. And again, there's some assumptions that we have behind correlation or calculating correlation, things that we assume. And we'll talk more about this as we get more into statistics. But here, right, our data should be a simple random sample, and they should come from a bivariate normal distribution. And again, a bivariate normal distribution is essentially a three-dimensional bell shape here. So we'll talk more about these distributions later in the course here. Okay, so here we want to calculate correlation here, or Pearson's correlation for the population. Here, this is denoted with a rho here for the population correlation, and this is just the covariance divided by this is the square root of the variance of x times the square root of the variance of y. And so this division here basically standardizes, right, our correlation here so that we can compare correlations between different data sets here. And then with the sample, right, this is our sample correlation. This is the formula. Right, again, numerator, this is just the formula for covariance. And down here in the denominator, these are just the formulas for the variance for x and y here. So again, this formula looks complicated, but really isn't quite that complicated here. So if we want to calculate the correlations for these two sets of variables that we've been looking at here, okay, here's our formula here. So if we were to calculate these correlations here, then what we need the mean, right, for the x's, the mean for the y's here, right, and then we can do the products just like we calculated correlation before, and then we just calculate the respective variances as well, and right, plug these in here. So we calculated the covariance before for this, and that was 20.5 here, and if we calculated the variances here, and we can do this in Excel, we'll go through an example in a little bit here. So we do this, and we actually find that our correlation is 0.959 for this first set. And again, remember, this measures the strength of the linear relationship here. So remember here, this first example, we had something that looked like this, right? So pretty good indication of a linear relationship, right? That this is a kind of fits on a line there. And if we calculate the correlation for the second set of data, here we get a much lower value of 0.356, and that's because here we're not something that's necessarily linear here, but again we had something that was more parabolic in shape or more of a quadratic relationship there for the second one. So the linear correlation or the strength of the linear relationship should be pretty low because it's not really a linear relationship in there. Right. Okay, so again, when we have correlations, we can talk about positive correlation. Again, positive correlation just means as x increases, or as one variable increases, the other variable increases as well. There, right? And so, we see some type of relationship like this. Right? So again, this is similar to the positive covariance. We can't have positive correlation without a positive covariance here. And then similarly for a negative correlation, right, we'll see something right that looks like this. Here, in this case here for negative correlation, again, as x increases here, or whichever variable this is this one increases, the other one is decreasing. Right? So they have an inverse relationship. As one goes up, the other goes down here for negative correlation. There. So again, that's similar, to what we see with the covariance here. And again, if two things are not correlated, then you'll see a kind of random scattering of points. Here, just a big blob of data. Here, right? Nothing. There. Right? So again, this is no correlation. Here, we just see kind of a random scattering of points. Here. So again, when we look at correlation, here when we calculate the correlation, here remember we divided by the product of the variances, and we did that to kind of standardize the values so we can compare. And what this does is it gives us a value between -1 and 1. So correlation, right, can't be smaller than -1, can't be larger than 1 here. And so, -1 is perfect negative correlation, and +1 is perfect positive correlation. And so when we talk about perfect correlation, this means that it is exact here. So right, that means that everything moves the same each time. If I have something that's perfect positive correlation, then right, it's going to look like this here. Okay. We get the same increase each time here, so we can draw a nice straight line through all these points here. Right? And that's perfect positive, and the negative would be down and to the right here. And so again, remember when we're looking at correlation here, right? We're looking at the relationship between two variables. Are they associated with each other here? And so we're looking at saying they're related, but we are not saying right that one causes the other here. So this is a real famous saying in statistics that people often tend to forget about, but it is that correlation does not imply causality. Right? We can see lots of relationships between variables, but it doesn't necessarily mean that one causes the other. It just means that they're related somehow, and it's up to us to kind of figure out what that relationship may be there. So, we get correlations, and we see all this time in the we see this all the time in media. There are correlations, and people talk about correlations, and so they want to point out that okay, since these are correlated, then one must be causing the other. Again, that's not necessarily the case there. Right? Okay, so again, once we look at correlation, remember correlation measures the strength of the relationship here. In this case, the Pearson correlation coefficient measures the strength of the linear relationship. And so another way we can use the correlation, or the Pearson correlation, is we calculate what we call the coefficient of determination. And what the coefficient of determination is, here, this is an R squared, right? So it's actually the correlation squared, and this tells us how much of the variance is explained by each variable. Right? So usually we talk about y here, how much of the variance of, about y is explained by x here. And really this really kind of pertains to, our modeling, and so we can look at it either way. right? Doesn't matter if we switch x and y around. Here, the r squared is going to be the same. So we can say, well, that's how much, variance that, y explains for x, or x explains for y here. And so here, again, remember this is our correlation formula, and if we square the correlation for the first one was 0.92 here, about 0.959. If we square that, we get about 0.92. So here we can think about this as what x explains 92% of the variance in y. And here, when we look at the r squared, remember our correlation here was about 0.356. We square that, we get a coefficient of determination, or an r squared of 0.13. So this is 13%. So here, x only explains 13% of the variation in y. And so one of the things I always like to do is to be able to explain, right, variation in variables. So, if we want to see, okay, how much, does this particular variable explain this variation, or vice versa, in here. So that's a nice number to keep in mind here. It's this coefficient of determination. Again, we'd like if it was really high. Again, strong correlations are going to give us high r squareds. Weaker correlations, or smaller correlations, here give us smaller coefficients of determination here. And so, again, when we look at correlation, remember this is between -1 and 1. So again, 1 is perfect positive, -1 is perfect negative. So, as we move towards each extreme, we're getting stronger correlations, right? And then, of course, the correlation of 0 means that there's really no relationship there. So again, the further we move away from 0, then the stronger, right, our correlations. Here, usually we prefer they be at least 0.5 is usually a good number. On the text, I think he starts as low as maybe 2.3 in here in terms of interpreting the correlation here. Where is it? Here it is. And so if you look on page 233 here, talking about the values of the correlation coefficient. So basically, anything 0.3 and above, they will interpret. Here, generally, 0.5. Once we get above 0.5, then we're starting to see a stronger, correlation there. So, usually 0.5 and above here is okay. That's still weak there, or you may go in the text as low as 0.3. That's a really weak correlation, but usually 0.5, and generally 0.7 and above is pretty good correlation between two variables there. And then again, anything above 0.9 is a really strong correlation in there, right? So again, when we look at this here, this is the Pearson linear correlation coefficient. And so another one we have is Spearman's rho, and this is what we call a non-parametric, right, measure of correlation. Here, this means we just don't make any assumptions about the distribution of our data. And this doesn't limit itself to just a linear relationship. Here, this describes how well that our data can be described by a monotonic function. And so monotonic just means that if it's monotonic increasing, that means that it goes up and it can level off, but it never decreases. So it's always increasing or staying the same, or it's always decreasing or staying the same. There, this is what we mean by something that's monotonic here. And again, this is really, we look at the correlation of ranks here. So we rank all the variables and see how the rankings correlate for each pair here. And again, since this is really correlation, then it's going to be between -1 and 1. So you can look through the text where they discuss Spearman's rank correlation. Here, usually you may see this referred to as Spearman's rho. as well here. So now, right, that we have this correlation here. This, again, remember, correlation measures the strength of the relationship. Now what we want to start to look at is, can we model this relationship?